Right, so first I'd like to thank the organizers for giving me the great opportunity to present my ideas in a 50-minute talk. And I'm going to talk about an analog of Kuratowski's characterization of embeddability to three-dimensional space. So Kuratowski proved that a graph can be embedded in the plane if and only if it doesn't have K5 or K3 as a minor. So this gives a way how embeddings in the plane could be understood using the minor relation. And a far-reaching extension of Kuratowski's theorem is the Robertson-Seymour theorem. And the structure theorem was the topic of Paul Woolen's talk, and it gives a deep connection, establishes a deep connection between embeddings of graphs in surfaces and the minor relation. And in 2006, Lovash Sr. asked whether there's a meaningful analog of this connection in 3 dimensions. And similar questions were asked independently by Matuszek and Wagner. Right, so a trivial remark about this question is that any graph can be embedded in 3-dimensional space. Just put the vertices in general position and embed the edges as straight lines. And Sergio already mentioned a non-trivial approach towards this question, namely just to restrict the number of possible embeddings we are considering, namely just to consider linkless embeddings. So this is not what I'm going to do today. Instead of restricting the number of possible embeddings we are considering, we want to put some additional structure on the graph. Namely, we glue some faces on some of the triangles of the graph. So we're interested in embedding 2-dimensional simple complexes into 3-dimensional space. So topological or equivalently piecewise linear or differential embeddings, all the same, embeddings of 2 complexes into 3 space. That's what we want to do. And the major breakthrough in that area was Rubinstein's algorithm, which determines whether a given 3-manifold is isomorphic to the 3-sphere. 2 complex is simply connected if any circle can be continuously moved onto a vertex using the faces. And I believe that already the simply connected case is a major case of the embedding problem. Because if you have a 2 complex that is embedded in 3-dimensional space, you can always add some faces within the 3-sphere to that 2 complex to make it simply connected. So the simply connected 2 complexes are phase maximal amongst the embeddable ones. And more recently, Matuszek, Sedgwick, Wagner, and Tanzer proved that the embedding problem of embedding a 2 complex into 3-dimensional space is decidable. And in a different paper, Matuszek et al. Said that they believe from all the embedding problems of embedding a d-dimensional simplicial complex into r-dimensional space, they believe that the embedding problem we are interested in, embedding 2 complexes into 3 space, is most important. Right, so to summarize, so far there are algorithmic results, but no structure theorems. Right. So I was able to prove an extension of Kuratowski's characterization, an analog of Kuratowski's characterization of planarity to 3-dimensional space. So more precisely, I found a minor relation on 2 complexes such that the class of such that these minor operations preserve embeddability in 3-dimensional space, and such that the following is true. So it simply connected, locally 3-connected, 2 complex can be embedded into 3-dimensional space if and only if it doesn't have one of finitely many excluded minors. And I'd like to mention that this theorem can also be extended from simply connected 2 complexes, from locally 3-connected, simply connected 2 complexes to 2 complexes that are just simply connected. Yeah, but I mean, this talk I'd like to focus on key ideas, so I'd like to have it in this version and define later what locally 3-connected means. And it also later gives some intuition how this minor relation is defined. Right, so in this real, like Kuratowski's theorem, because a two-complex is embeddable under these conditions if and only if it doesn't have one of finitely many excluded minors. And one of the excluded minors appearing in that list is the cone over K5. So you start with K5, and then you take the cone over K5. And similarly, as K5 is not embeddable in the plane, the cone over K5 cannot be embedded in three-dimensional space. So suppose, for a contradiction, it was embeddable in three-dimensional space. Now take the top of the cone and consider a ball around the top of the cone. Then the cone would intersect that ball in a K5. But that's in a contradiction because K5 cannot be embedded in the two-sphere. And another construction to embeddability is constructed as follows. So you start with the octahedron with its 8 triangular faces. And now we want to add 3 more faces to this octahedron. And these 3 more faces are orthogonal to the 3 axes. So one orthogonal to the x-axis, one orthogonal to the y-axis, and one orthogonal to the z-axis. So if we just have the octahedron, there's just some embedding drawn on the right-hand side. If you just have the octahedron with the 8 triangular faces. And if we add 1 more face, we can just embed it on the inside. And this you see on the right-hand side, if you're embedding of the octahedron with 1 more face. And now if we add a second face, we can add it on the outside of the octahedron. But as it turns out, if you want to add all 3 faces at the same time, then this is no longer possible. I mean, there's a picture on the right-hand side. And the cone over K5 was a local obstruction to embeddability. Local in the sense that you could look at the neighborhood of a particular vertex and already from this deduce that you cannot embed. For the octahedron obstruction, this is not true. If you look at a particular vertex, there's always one face that doesn't, every vertex doesn't see one of the newly added faces. So if you just look at this vertex, locally it's embeddable, because if you have the octahedron with just 2 faces, it is embeddable. So locally at every vertex, the octahedron obstruction is embeddable, but it's not globally embeddable. So, perhaps the most well-known examples of 2 complexes that cannot be embedded in 3-dimensional space are triangulations of the Klein bottle or the cross cap. And the next theorem, the cross cap, appears as one of the obstructions to embeddability. And now we weaken the assumption that the 2 complex is simply connected to just assuming that the first homology group is trivial. So now we have a, locally 3 connected 2 complex with the first homology group being trivial. And then the 2 complex can be embedded in 3-dimensional space if and only if it doesn't have one of these finitely many excluded minors and it's simply connected. Right, and already in this theorem, we have now infinitely many obstructions to embeddability. And they are constructed as follows. So you just have a single vertex. You just have a single edge, which is a loop. And now you attach a face to it, which q times traverses that edge in the same direction. Right, so that's now, for q greater than 2, this is an infinite list now of obstructions. So in general, there must be infinitely many excluded minors for the 3-sphere. So now I'd like to prove a bit, talk about and give an overview of the proof of the first theorem. So the theorem that we had a locally 3 connected 2 complex, and said that it's embeddable if and only if it doesn't have one of finitely many excluded minors. Right, so the first step is as follows. So assume you have a 2 complex that is embedded in 3-dimensional space. Then for every edge, you have a cyclic orientation of the incident faces. in the embedding. Right? The embedding induces at each edge a cyclic orientation of the incident faces. And at each vertex, we consider a ball around that vertex, in two balls around that vertex. Every edge intersects that two ball in a vertex, and every face intersects that two ball in an edge. So we get a graph drawn onto that two ball. So if the two complex embeds in the three sphere, then we get induced embeddings of graphs in these two balls. And these graphs can be defined independently of the embedding. Namely, they're just the incidence graphs between the edges and the faces. Right, so to summarize, if your two complex is embeddable, you get a rotation system, so the cyclic orientation at all the edges of the incident faces, that at each vertex projects down, so this cyclic orientation of the incident faces projects down at every vertex of the complex. So the edge projects down to vertex, the faces project down to edges, and then in these embeddings of these graphs, which we call the link graphs, then in the embeddings, these cyclic orientations at the edges agree with the embeddings in the link graphs. Right? So very roughly, if you are embedded in 3 space, then you get these rotation systems that at the vertices satisfy some planarity conditions. And that's what we call a planar rotation system. But this process also works the other way around. So if you have a 2 complex, together with such a planar rotation system, then from this you can build some 3-dimensional manifold. And it's easy to check that if the 2 complex you start with is simply connected, then so is the 3-dimensional manifold. Proving the Poincaré conjecture, Perelman proved that if you have a compact 3-manifold that is simply connected, then it must be isomorphic to the 3-sphere. So if we use this, if we combine this with the theorem above, then we can deduce that the 3-manifold we construct actually must be the 3-sphere if the 2 complex is simply connected. Right, so all that remains to show is to give a combinatorial characterization of which 2 complexes have these planar rotation systems. All right, and now I wanted to tell you what locally 3-connected means. So it just means we defined these link graphs at the vertices, which were just the incidence graphs between the vertices and the edges. Right, and locally 3-connected just means that all these link graphs should be 3-connected. Yeah, and as I said, so the theorem also extends if we don't assume that we're locally 3-connected, but there's some more technicalities. And in this talk, I'd like to stick to the 3-connected case. Right, so let me summarize the rough overview of the proof. So first, we show that embeddability is equivalent to the existence of certain rotation systems. And then we use Perelman theorem to deduce that the actual embedding we construct must be an embedding in the 3-sphere if the 2 complex is simply connected. And then, the last step about which I really didn't talk is then to give a combinatorial characterization in terms of excluded minors of the existence of these planar rotation systems. Right, so still you're all still all with me, but if not, then this is a good point to jump in again. Right, so now what? So far we have seen 3 types of obstructions to embeddability. So the first were the local obstructions, like the cone over K5 or K3. And then we had this global obstructions, and the third type of obstruction came from the difference between homology and homotopy. But there are even more obstructions to embeddability, constructed as follows. So you start with the 4 by 2 by 1 grid, so just as depicted in the figure, and now you glue faces on all the 4 cycles of that graph. And this then gives you a 2 complex. And here you just see an embedding of that 2 complex in 3-dimensional space. But now what we're going to do is to take the 2 red edges, so just in the figure, take the 2 red edges and identify these 2 red edges. And you can't do that kind of preserving an embedding in 3 space. And as turns out, actually, when you identify these 2 red edges, you are no longer embeddable. Somehow these faces have to cross. And to study obstructions of this type, we work inside the class of nearly simply connected 2 complexes. So these are obtained from locally 3 connected, simply connected 2 complexes by identifying vertices and identifying edges. And already inside that quite restricted class of nearly simply connected 2 complexes, we can construct infinitely many obstructions to embeddability. So already inside that quite restricted class, so just simply connected, locally connected, plus these identifications, you already get infinitely many excluded minors for the 3 sphere. But on the other hand, if additionally you put some global 3 connectedness assumption on the 2 complex, then you just have finitely many excluded minors. So if you have a nearly simply connected 2 complex that is globally 3 connected, then it's embeddable in 3-dimensional space if and only if you don't have all of these finitely many obstructions from before plus 6 more. Right, so now let me finally talk about what this minor relation is and how can you define them. Right, so I mean, one property of this minor relation we'd like to have is that in certain situations it corresponds to taking minors in the link graphs. But this is not enough to say how these minors are defined. And right, so what we additionally would like is to have is that, right, so is the following. So suppose your 2 complex is embedded in 3-dimensional space. Then you can define the dual graph of the embedding. Namely, for each component of the embed, right, so you take now the 3-dimensional space, say S3, yeah, you take S3 with the 2 complex embedded, and for each component of S3 with the 2 complex removed, you draw a vertex. And for any face, I mean, each face now attaches for 2 of these components, and you draw an edge joining these 2 components. Or if it just goes at 1 component, you just make a loop at that vertex. So that's the dual graph of the embedding. And what we'd like is that some of our minor operations correspond to taking minors in the dual complex. But the problem is that dual graphs depend on embeddings. So they might not be uniquely defined, or even worse, if the 2 complex is not embeddable, then they just don't exist. But this phenomenon already arises in 2 dimensions. So here's so it's right. So there's just one graph, the black graph, but we have drawn 2 different embeddings. And in one embedding, the dual graph has a vertex of degree 6, and in the others, all vertices in the dual graph have degree 5. Right? This we all know. If you embed graphs in the plane, they need not have unique dual graphs. And you also all know how to resolve this. Namely, Whitney observed that although graphs do not have unique dual graphs, any 2 dual graphs always have the same edge sets of cycles. And the edge sets of cycles can be rephrased in terms of the primal graph. Namely, they are the edge sets of bonds, minimal non-empty cuts of the primal graph. Right, and that's his definition of the dual matroid of a graph. So the dual matroid of a graph is just a set of bonds. Right, so it's just a set of bonds of that graph. Right, so now let me come back to the problem we had. So we had the problem that the dual graphs of the embeddings are not always uniquely defined. But now we can do the very same thing as in 2 dimensions. Namely, we can define the dual matroid of a 2 complex. And now we just define the minor operations so that they correspond to the minor operations in the dual matroid. So let me make this more precise. Right, so if we contract an edge in the dual matroid, this corresponds to deleting a face in the simplicial complex. Right, so one of our operations is deleting faces. And now if we contract an edge, contracting an edge in the matroid, in the dual matroid corresponds to deleting a face. And now what corresponds to deleting an edge in the dual matroid? So if the face of the 2 complex that corresponds to that edge, so here we have the face of 2 complex, and here we have the edge in the dual matroid. If the face in the 2 complex just consists of 2 edges, so just has size 2, we can just identify these 2 edges along the face. Right? So if it has size 2, then you just do this, right? So you just identify the 2 edges along the face. And this corresponds to deleting the edge in the dual matroid. Right, so but it's unclear how you should define that if the faces have size 3. But it's an outcome of the proof that you never ever have to define it for faces of size 3, but you can always, it is enough to define it for faces of size 2. But in addition, you need also some more operations, such as contractions of edges that are not loops. But now you have to be careful. I mean, if you contract too many edges and you have a face of size 3, then it can contain 3 loops, and then you're no longer allowed to contract that face, right? You're only allowed to contract faces of size 2. Right. So you have to be careful with the contractions, but somehow you can kind of combine that in a nice way so that it's enough to do these contractions. Right, so let me point out 2 more advantages of this Matroid perspective. Right, so Whitney proved that a graph can be embedded in the plane if and only if its dual matroid is graphic, that it's a cycle-matroid of a graph. So it might be natural kind of to ask whether we could just kind of have the same theorem, say, for simply connected 2 complexes. So is it true that if we have a simply connected 2 complex, such that the dual matroid is graphic, is it then always true that it can be embedded in 3-dimensional space? But it's not true, and here's an example. So just the cone over K5 we had before. I mean, it's not a hard computation to see that if you take the dual matroid of the cone over K5, actually it's just the sum of loops. Because if you look at the edges on the K5, they're just incident with a single face, and this just says they are just all loops. So the dual matroid is too rough to kind of capture the local structure at the top of the cone. So this global matroidal dual structure is too rough to kind of see this thing that's going up at the top of the cone. But if we exclude that, and I wrote the precise definition down there, so we just call it local, but I won't define it, but yeah, it can be made precise. Right, so so now you have a simply connected 2 complex, and you assume that your dual matroid is local, then this can be complex can be embedded in 3-dimensional space if and only if the dual matroid is graphic. Right, so just like Whitney's theorem. And then, I'm then using a theorem of Tutte. This is then, of course, equivalent to that the dual matroid doesn't have one of these 5 matroids, dual of K5, dual of K3, the Fano, the dual Fano, or U24 as a minor. Right, so now let me come back to this example we had. So we had this 4x2x1 grid, and where we had the 2 red edges and identified them. And I said, yeah, this cannot be embedded in three-dimensional space. And now actually using the dual matrix, we can actually prove that. Right, so if we take the two complex before we identified the two red edges, right, then this is the dual graph of the embedding I just drew, right? I mean, you have the 8 kind of, the 8 components in the middle, which correspond to the 8 cubes, and then you have one component on the outside, which is the vertex on the very right, right? So that's the dual graph of that complex. Right, so now, what you can just compute is if you identify the two red edges, you still have the same dual matroid. And actually, it's still represented by that graph because that graph is reconnected, so it's a unique graph representing that matroid. But if you have a two complex that is embedded in three-dimensional space, and then you have all the faces incident with that edge, then each of these faces is an edge in the dual graph. So all these edges in the dual graph form a closed trail, right? I mean, very often they form a cycle, but in general, they just form a closed trail. So in particular, the set of these faces incident with the red edge must be connected edge set in the dual graph, right? If you have the edge here and all the incident faces, then all these faces on the dual graph a connected edge set. But as you see, if you kind of have the two red edges here, and then you have like 4 faces incident with each of them, and if you look what they are in the dual graph, they're just the union of 2 4 cycles, so they're not connected. Right, but this means that this two complex cannot be embedded in three-dimensional space. Because if it was embeddable, then this red set must be connected, but it's not. Right, so similar as for Kuratowski's theorem, there's now a linear time algorithm that decides whether a simply connected two complex can be embedded in three-dimensional space. But it also goes the other way around. So if you have a two complex that is simply connected, you can decide in linear time whether, if you have a two complex that is embedded in two-dimensional space, you can decide in linear time whether it's simply connected. Right, so now I'd like to talk about the following lemma, which appears in the proof of our theorem. Right, so the situation is like this. So you have a two complex that is embedded in three-dimensional space, and you'd like to deduce that all components of the embedding are balls. Right, I mean, okay, so right, that's what you like to deduce, but it will not be always true. So for example, it might be that your two complex is just a triangulation of a torus. Then one of these components will not be a ball, but it will just be the interior of a torus, right? But the torus has some the torus has some genus reducing curve that cannot be contracted in the torus to a point, right? Say another way, the torus is not simply connected. And what the lemma says is if you now assume that you have a two complex that is simply connected, embedded in three-dimensional space, then all components of the embedding must be balls. So they cannot look like torus. They really must be balls. Right? That's what the lemma says. Right, so how do we do the proof? Right, so and for the proof, we need the dual complex of an embedded complex. We already defined the dual graph of embedding. How do we define the dual complex? Right, so we define the dual graph by taking one vertex for each component of the embedding and taking one edge for every face of the embedding between the two components that contain that face. And now we want to add some faces on the dual graph. And we add one face on the dual graph for every edge of the original complex. And what are the edges incident with this face? I mean, the edges of the dual graph are faces in the original complex, so they are edges. They're edges in the dual complex, and you just take that set of edges. Right? Just to say differently, so you start with the dual graph, and now you add some faces, and the edge-face incidence relation in the dual complex is the same as in the original complex, but with edges and faces interchanged. Right? And whenever you have a 2 complex embedded in 3-dimensional space, you can also from this construct an embedding of the dual complex. And the condition that all components of the embeddings are balls translates to that if you look at the vertices of the dual complex, then the link graphs get embeddings in the plane. I mean, that's kind of intuitively clear, right? I mean, you want that the components are balls. So in the dual complex in the link graph, you want that the link graphs are embedded in spheres. I mean, I won't go into details, but kind of from the picture, it should be kind of clear. And that's what we are going to prove. So we want to prove that in the dual complex, the link graphs are embedded in spheres. Right. So the next step in the proof is to consider the following alternating sum, which is remnant of Euler's 3-dimensional formula. So number of vertices in the complex minus edges plus faces minus vertices in the dual. And we would like, now we use some linear algebra computation to show that this is always greater or equal than 0. Right, so how does it go? So let's assume the 2 complex is simply connected. So the number of vertices is the size of a spanning tree, plus minus 1. So vertices minus edges is plus minus 1, the number of edges that are not in the spanning tree. And this is just the dimension of the cyclespace, plus minus 1. And similar in the dual. So the edges of the dual are the faces of the original complex. So faces minus vertices of the dual is the dimension space of the dual, plus minus 1. And now we use the fact that we are simply connected. So if we are simply connected, every cycle is generated by the phase boundaries. So the dimension of the cycle space is equal to the rank of the edge phase incidence matrix. Right? That's what simply connected says. But we don't know yet that the dual is also simply connected. So we cannot deduce that the dimension of the cycle space of the dual is equal to the rank of the edge phase incidence matrix of the dual. We just get an inequality there. But the edge phase incidence matrix of the complex is the transpose of the rank phase incidence matrix of the dual. So because row rank is equal to column rank, they have the same rank. So because in one thing, on the left-hand side, we have an equality. On the right-hand side, we have an inequality. So we get the inequality overall. Right, so the next step is now to use a topological argument to show that we also get the inequality the other way around with equality precisely what we want. Namely, we already translated the condition that we had to the condition that in the link graph, in the dual graph, all links are plane. And yeah, right, so this is all that remains to prove, because then we can combine it with the step above. So we then have equality, and then we just get the conclusion we want. So let me show you why this is true. Why it's less or equal than 0. Right, and for this, we apply now Euler's 2-dimensional formula in all the link graphs. Right, so we have this complex C embedded in 3-dimensional space. And we know that all link graphs are embedded in the sphere. So we can apply Euler's 2-dimensional formula there. And we're going to apply it at every link graph and take the sum over all these formulas. And we have one link graph for every vertex. So if we sum over all of this, we get 2 times number of vertices. On the other hand, the vertices in the link graphs are the edges of the original complex. And each edge appears in 2 link graphs, namely its 2 end vertices. So if we take the sum over all the vertices appearing in these formulas, this is precisely 2 times number of edges. And the edges of the link graphs are the faces of the 2 complex. And each face appears precisely in its degree many link graphs. And it doesn't matter whether we take the number of incident edges or number of incident faces, because it's just the same. So the sum over all the edges that appear in this formula is the sum over all degrees of these faces. That's the number of all edges appearing in these formulas. And then we have the sum over all faces appearing in these formulas. Yeah, let me just denote it by x. And that's, yeah, I won't go into details there. All right, so that's kind of the error term we have at the end. And now we do the very same trick, but we now do it in the dual complex. And we don't get an equality there because we don't know yet that all link graphs of the dual complex are spheres. We just know they're connected, so they're just some two-dimensional surfaces. But we don't know what they are, so we just have an inequality there. And the edges of the dual complex are just the faces of the original complex. So we have in the second term of faces. And then, yeah, also here, edges and faces interchange. So the sum over all the degrees of the edges, meaning the number of incident faces of these edges. Right, so, and now these two sums actually cancel out, because what do they count? They count the number of non-zero entries of the edge face incidence matrix. And the edge face incidence matrix and the transpose have the same number of non-zero entries, so actually these two sums are the same. And now we just take the difference between these two formulas. All right. And I should tell you that also these two error terms are the same, but I mean, I didn't talk about them anyway, but I think that's some further computation I'm going to skip. All right, so let's just ignore that. Somehow they cancel out. I didn't tell you why. All right, so they cancel out if we take the difference. Then these two sums cancel out. And then we're going to divide by 2, and then we get precisely number of vertices minus the edges plus the faces minus number of vertices is less or equal than 0. And when do we get equality? We get equality precisely when we have equality in the second, in this equation here, and there we have equality if all the link graphs of the dual complexes are actually spheres. And that's this last part here. All right, so let me summarize. So first, we translated the condition that all components of the embedding are spheres to a condition about the dual complex. And then we considered this alternating sum, which looks like Euler's formula. And on one hand, we used the linear algebra computation to show that it's always greater or equal than 0. On the other hand, we used the topological argument to show that it's always less or equal than 0, with equality precisely when we have the condition that we wanted. Right, so far there were some algorithmic results, and now we proved some Kuratowski type characterizations of embeddability, which lead to efficient algorithms. In the proof, we use Perlman's theorem as a black box, and methods from Matroid theory, topology, and graph minus, and in total it's more than 100 pages. Right, okay, right. So, I mean, the natural question, I mean, could we extend this somehow to higher dimensions? Or, I mean, there are lots of characterizations of embeddability in the plane, so how do they extend to 3 dimensions, and what relations do these extensions have between them? So a homology sphere is a manifold with the property that its that all its homology groups are the same as for the 3 sphere. And unlike in 2 dimensions, in 3 dimensions, there exist homology spheres which are not isomorphic to the 3 sphere. And these then give rise to excluded minors for the 3 sphere. And we have no understanding how they look like. So in particular, we just don't know whether there are infinitely many homology spheres that give rise to excluded minors. We don't know. And that's, I mean, yeah, the last thing is perhaps very ambitious. I mean, I said that in our proof, we used Perlman's theorem as a black box to deduce our Kuratowski theorem, but it also goes the other way around. So from our Kuratowski theorem, we can actually, not with a lot of effort, deduce Perlman's theorem. And yeah, I mean, it would be very ambitious, but I think it would be very interesting to find independent proof of that Kuratowski theorem, which then would give you a combinatorial proof of the Poincaré conjecture. Yeah, thank you.
Are there any questions? Rose?
Do you have a notion for when there may be unique duals?
Sorry?
Do you have a notion or a guess for when there may be unique duals? Like a notion of connectivity, so that there's duals that are unique at isomorphism. I wonder if that's possible.
Wait, what do you mean by unique duals? I mean, the dual matrix is always uniquely defined, right? So perhaps, I don't know whether that answers your question, but then if the dual matrix is reconnected, then kind of it will represent a unique graph. Yeah.
Did you say that it's not known if there's infinitely many different homology spheres? No, there aren't.
There are infinitely many, but I don't know whether kind of using these minors, you can make them the same. I also didn't think too much about it. I mean, probably it's easy to construct an infinite family there.